Hello everyone, and welcome to today's webinar. On behalf of Tornado Spectral Systems, I would like to thank you all for attending. I'm your moderator for today, Omar Bassi, Marketing Associate at Tornado Spectral Systems. Today's presenter is my colleague, Jeremy Linoski, Senior Instrumentation and Application Specialist. Following his presentation, we will move into a live question and answer session where you can pose questions to today's webinar. You can submit questions using the chat box within the menu. Now, before we begin, a quick overview on Tornado Spectral Systems. We're a leading manufacturer of optical spectrometers and systems, largely for Raman spectroscopy. We're headquartered in Toronto, Canada, where we have our manufacturing and R&D teams, as well as several field offices across the US. With worldwide distribution, our list of distributors continues to increase as we expand into new markets. HyperFlux is our major brand. Our spectrometers deliver significantly enhanced sensitivity by using a patented high-throughput virtual slit, and Jeremy will be expanding on this during his presentation. HTVS, the technology that is, was patented and conceived in 2006 and eliminates the physical slit of a conventional spectrometer. We cover many high-performance markets, and our products are CE, ATEX, and UL certified. So about our speaker, Jeremy has significant experience within the development, validation, and implementation of NIR technology methods. In addition, he has extensive knowledge within vibrational spectroscopy. His expertise includes multivariate analysis, Raman, CGMP compliance, and so forth. Furthermore, he has published numerous application and technical notes and given presentations at various international conferences. So without hesitation, may I pass you on to today's speaker, Jeremy Linoski.
Right. Thank you, Omar, for that introduction, and I want to thank everyone who is in attendance. I know we all know how valuable your time is, so I really do sincerely appreciate that you've given some time out of your day to allow me to speak to you in this webinar about high-throughput virtual slits technology's impact on Raman spectroscopy limit of detection performance. This presentation reviews the detection limits and corresponding minimum required acquisition times of tested 4 binary mixtures using Tornado's HyperFlux Pro Plus Raman spectroscopy system. And it will demonstrate its better sensitivity for lower detection limits, doing so at faster measurement times, which in turn enables it to be more feasible to deploy for real-time process monitoring applications. So first, I'll start off by an overview of the instrumentation used for the study, the core of which is the spectrometer. And this study featured Tornado's HyperFlux Pro Plus single-channel fiber optic process Raman analyzer that employs a USB to PC connection. The Pro Plus uses an optimized HTVS design that provides equal to or greater than 10 times the optical throughput in comparison to other process Raman systems, while doing so at a significantly less footprint, the actual size of the spectrometer. The pictures that I'm showing here, our collection fiber is actually a 300 micron core. It's one of the secondary benefits of HTVS is to enable a larger collection fiber, a bigger diameter, allowing more photons to be transmitted over a given distance. The excitation delivery fiber has a 105 micron core. The laser power is configurable between 10 to 495 milliwatts. We decided to have a maximum of 495 to ensure that the laser power does not exceed 500, which that keeps it a Class C system. Above 500, we then have a different laser classification of Class 4, which has different requirements that one would have to be concerned with. The excitation source frequency is a 785 nanometer. The spectrometer has a spectral range of 200 to 3,300 wave numbers, with over that range a better than average resolution of 5 wave numbers. And we see here at the bottom showing both the size and the weight of the spectrometer, both in the US and metric systems. We have the spectrometer and the fiber optics, and this we also need a sampling interface, and that being the probe. Spectra were acquired with the use of a Mark Metrics immersion ball probe. The schematics of which were had a half-inch diameter and was 6 inches in length. A ball probe is a patented backscattering immersion probe that has a sapphire ball lens and a rigid Hastelloy housing. Again, this manufactured by the company, well-known company for high-performance Raman probes known as Mark Metrics. So next, addressing the sampling environment. With optical measurements, the Raman infrared, often you have to take a background measurement. In this case, a Raman would call it a dark, and that's to compensate or to address potential ambient light variations. If one way is if we can shield that from those lighting variations, one can take a dark scan, which would map the given lighting conditions, but if they were to vary with time, if there was those variations were to occur during the course of the acquisition, then the dark scan may not be representative, and that would enforce you for ongoing measurements, to have to take a dark scan more frequently. So in order to maybe to avoid the requirement for that, if you're to optically shield the environment from those variations, you simplify the measurement. So here's a case of showing the part and model number of the black hardboard enclosure that I used, that I purchased from Thor Labs, that all the sample measurements were conducted in. Next, discuss my experimental design. In discussing design, it's worth to note what the purpose and some background associated with that. The first is we're talking essentially about detection sensitivity, which is related to the amplitude of the signal and the noise. SNR, signal-to-noise ratio, is a measure of that signal strength relative to the background noise. And most things, we want it the higher the better in regards to that ratio. The signal can be increased by collecting more photons. That'd be more light that's returned scatter by the sample when exposed to the laser energy. And it's such that the Pro Plus was an ideal system for that, and then we have an enhanced photon throughput, and ultimately I'll show through the course of the study how that results into better sensitivity, as well as in combination doing so at decreased exposure time requirements. The next part of the address, we talked about the signal. Now let's discuss the noise. Noise is the part of the measurement due to sources other than the component of interest. And in that regard, we want that to be as small as possible. We can prove SNR by, like I said, increasing the numerator while decreasing the denominator, that being the numerator of the signal and then the denominator of the noise. As we increase the signal, and of course there ultimately is a limit there, we want to make sure we don't at some point could oversaturate the detector or reach areas as we approach detector saturation that can create nonlinear properties in the data. But once we've maximized our ability within a good exposure, not saturation, not in the linear range of the detector, we want to improve our SNR further. We can do so by decreasing the noise. And that is because as we increase the signal, the noise increases, but not at the same rate, lesser so. This then gives us the secondary opportunity of employing averaging of multiple scans to make reductions in the noise level. And that is because it's the inherent random in noise itself that makes that useful. As we have a series of data around a mean, if there's a randomness of data, the positive, if we do averaging, adding them up and dividing, the positive and negative values begin to cancel each other out. So then with the further averaging, we thereby can further reduce the noise level and improving the overall SNR. Mentioned this is particularly the focus of this presentation with regards to quantitation is focused on limited detection. which is defined as the lowest quantity of a substance that can be distinguished from the absence of that substance, that being the blank. The extent of which how low we can get in terms of limit detection is going to vary on a number of things. One, what is it we're looking to quantify, the target, and specifically in regards to Raman. The larger its Raman cross-section, which generates more Raman energy or return scatter photons, the better the opportunity that provides to detect it at lower levels. But ultimately, even that information by itself is still not all-inclusive, as we need to know what matrices it is that it's in. If it's in the presence of other strong Raman scatterers that have spectral peaks that overlap the target component's peaks, that could limit our ability of how low we can detect. Or if there's noise characteristics data, like even like chemical noise fluorescence could mask that signal or reduce its contribution relative to an overall baseline. So all those things will always be a case-by-case basis. For this reason, I wanted to perform this more than just one. So I did 4 binary mixtures that I would prepare a range of concentrations ranging from 10,000 ppm, 1% volume, to 10 ppm, that being 0.001%. And I would do so by setting up a series of dilutions to obtain an average of 15 including basically the blank, to encompass this range from 10,000 to 10, essentially 0 ppm. Power that was set for the LoD Plus was 495. It's maximum power setting. But this is, we're going to transmit our fiber optic. The probe itself will have an influence on how much laser energy ultimately reaches the sample. And it is that energy that's creating the excitation in the Raman mixture. So it's important to measure that to understand what is the actual power epic, because different probes can, even if the instruments the same power, can have an impact in that regards. So in this case, I took a coherent, high precision, high accuracy laser power meter, and that was measured to be 248 milliwatts at the probe tip. As to the sample acquisition, spectral acquisition parameters, for each mixture, the exposure setting was first optimized to maximize the peak intensity of the target component's most significant peak that was best resolved from that of the diluent. So I'd focus my attention as to optimize the signal strength on that given peak, and not necessarily the overall, all the peaks of the sample. For each calibration concentration sample prepared, I would acquire 20 individual spectra that in the software we refer to as SpectraSoft, the Pro Plus acquisition software. I would set up predetermined averages in the case of 25 for the benzene and acetone mixtures, and 15 for the propylene glycol and sodium nitrate. So essentially it was 20 the files once generated, or SPCs. It would be 20 SPCs based on a 25, for example, exposure average already determined by the software. So if the exposure was determined to be, requirement was at 300 milliseconds, SpectraSoft would acquire 25 of those and process that into a single SPC file. And that SPC file then is representing, in terms of its total acquisition time, exposure but acquisition time of 7,500 milliseconds, meaning 7.5 seconds per spectral scan generated. From there, I could then test as configurable greater averages using the offline via software package, a combination of MATLAB and PLS Toolbox. So if, for example, I wanted to test a 50 average co-added spectrum, that would be I would take 2 of the SPC files, each representing 25, and average those into a representative SPC file, which is therefore the equivalent of a 50 average equaling the acquisition time of 15 seconds. From there, with the acquired data, I would build 3 calibrations, PLS calibrations. over the full concentration calibration set of 10,000 to 0, and then 2 more where the concentration range was narrowed to 750 and the other 250 and below. That is, as with multivariate calibrations, if you can narrow the range, you can often improve the precision and accuracy of the measurement. It can better map those smaller variations in the data, that being spectral data in this case. The predictive accuracy was compared in terms of the resulting performance as either RMSEC, root mean squared error of calibration, for the maximum exposure. That's where the full 20 was averaged into the single representative spectral file. And then RMSECV, so the standard error of cross-validation, when then I was dealing with the smaller replicates, either single or averaging of the 2 or the 3 and so forth, because then I had replicate data, and therefore I could do something like leave one out cross-validation. In each case, the maximum exposure obtained by the full 20 spectral file combination into a single representative spectrum was considered the optimized for minimized error. As I said, this could be up to 500 replicates, essentially, of the individual exposures. And then from there, when looking at the smaller averages, the lowest acquisition time that maintained the same relative approximate RMSECV as the RMSECV, but also in regards to its precision, was determined as to, therefore, would mean the desired optimum performance. For all the data sets, I did evaluate different pre-processing, but actually found this is all that actually was required. But it was also, I found it helpful if I kept that as a constant. So we're really looking at the generalities of, also we're looking at just HTVS its performance as a whole, versus just trying to tweak every little individual calibration just to optimize and lower the overall predictive error. But like I said, in the end, after testing all these, I actually found this is all that was actually quite necessary. And that is, I use this Fisky-Golay first derivative with an 11-point filter as the only pre-processing you do to compensate for baseline variations. And with the multivariate and spectral data, everything was, of course, always mean-centered. I'm also a big proponent for not overfitting the data and falsely reporting over-optimistic predictions. So I always visually and carefully inspected each loadings associated with each latent variable, or aka factor, depending on your chemometric background and chemometric software they're used to using. To do so, it was to avoid any incorporation of noise in the data, thus overfitting it, and therefore in turn underestimating the true predictive error performance of the calibration. So the first of the matrices that I'll be reviewing is benzene diluted in isopropyl alcohol. Here's below is a spectral plot of the maximized 300 millisecond exposure of the highest concentration, 10,000 ppm of benzene in IPA, which is overlaid with the pure 50 millisecond benzene and the 50 millisecond exposure of IPA. And like I said, I use this often as an informative tool to help me decide, again, when I mention about what peak to optimize the exposure on, as well as the PLS calibration as well. And as I'm a big proponent of not overfitting the data in terms of the incorporated latent variables, also a big proponent of not using full spectral calibrations, where you want the signal in the calibration to be predominantly of the target of interest, avoiding any other areas of spectrum that may independently correlate for the given time of the calibration set, but then, of course, in a real setting, particularly in a production run, may not, and so you'll get erroneous predictions by the inclusion of more spectral peaks that are not related to the direct impact of the chemistry of interest. So the spectral ring used for the benzene IPA calibration was selected to be of 970 to 1020 wave numbers. And here I have the green is showing the kind of the highest, middle, and of course Planck calibrations to see where the variation of benzene comes into play. So here's a summary of the mention of the 3 calibrations that I would do for each test set. I said not overfitting the data. It was only at most 2 factors that were ever incorporated in the calibrations, and yet all achieved a very good R-squared. For all 3, the minimum, so I was really probably too conservative when I set the initial 25 average. Probably could have got away with much smaller, but each single replicate of the 20, which was a 7.5 second total acquisition time, maintained the same relative predictive error as the maximum 150 second average scan. So there's no further gain over essentially the 25 than doing further and further averaging. Within doing so, for the full range calibration, had a average predictive error of 35 ppm. With the order of magnitude of the limit of detection of around 104 ppm. The reduced range calibration is 750 and below. We improved it down to 11 ppm with a rough 33 ppm limit of detection, and then again you can prove it slightly even further by reducing it down once more to the 250 below and getting a smaller improvement to roughly an 8 ppm average predictive error and resulting 24 ppm limit of detection based on the cal bias plus 3 times the predictive error. Next, looking at acetone and ethanol. The plot provided below is the maximized 1500 millisecond exposure of the 10,000 ppm acetone and ethanol sample spectrum, overlaid with the 60 millisecond acetone and 120 millisecond ethanol spectrum. From there, I determined that the calibration range that I would employ would be 760 to 820 wave numbers. And for the full calibration model, only required 1 latent variable, that being 1 factor, with an average predictive error of 32. And determine limit detection around 100 ppm, 95 to be more precise. And in this case, the 37.5 second average maintained the same predictive statistics as did the full maximum 750 second average. But now we can start seeing some of the differences when you're looking at additional averaging. It was then determined that a 187.5 total acquisition average maintained the requirement that I had or needed for the 750 predictive to be in agreement with the 500 second average. None of the, for example, the 37.5 and so forth, smaller time interval averages didn't result in satisfactory equivalent predictive error or precision. But on the 187.5 acquisition total, 2-factor models with predictive errors, the RMSECV of, round up a little bit, 17, with a limit detection, then calculated to be about 50, and down to around 8 predictive error with again around the 24 to 25 ppm detection limit. Next, I looked at, so it kind of went down in terms of the Raman cross-section. So this is now propylene glycol and water. One of the advantages of Raman is that water, things that have a strong dipole movement, polar molecules are not strong Raman scatterers. So often Raman, which can be a problem in infrared, if you have a dilute material in water, it can prevent the measurement, quantitative measurements, particularly at low concentrations. Raman's good for that. We have the spectrum here of the 2,000 millisecond determined exposure for propylene glycol in water, overlaid with the 100 millisecond exposure scan of propylene glycol and the 1,000 millisecond of water. Again, I wanted this for overlay purposes and helping determine the spectral range to use for the PLS calibration. Here that propylene glycol is really the primary contributor to the spectral peaks that we've seen, so I could use a larger spectral range, which I did, and was set to 760 to 1540, 1540 wave numbers. So for this test set, the 30-second average, because remember these were larger exposure times, but I set to a smaller predetermined minimum average of 15. The 30-second acquisition time maintained the same relative predictive error as the maximized 600-second average. Two-factor model with a rough limit of detection. The LoD calculated based on the predictive error of 69.5 at 208 ppm. When I looked at then reducing the calibration to improve the lower detection limits for using the reduced calibration ranges of 750 and below and the 250, there was determined that it did not result in any satisfactory accuracy or precision. So rather it may either be the maximum or even the reduced averages would not produce satisfactory result. What I take in from that was, again, as you get to things that are weaker, smaller in terms of the Raman cross-section, therefore weaker Raman activity, PLS calibrations need spectral variation to map that variance to perform the prediction. So at these much lower concentrations, there wasn't enough spectral variance in the data to really accurately model. So really you need to have the calibration of this full range, which ultimately in some regards keeps you at a higher limit of detection. And last, the fourth was sodium nitrate and water. Here we have a more defined, really strong signal peak to work with. This was similarly with the propylene glycol, determined that the 2,000 millisecond exposure was the desired signal strength. Again, overlaid now in this case it was 75 millisecond of the solid sodium nitrate sample with again the 1,000 millisecond water spectrum, representative spectrum. So therefore the spectral range in this case is much narrower than by comparison to the propylene glycol. We used a range of 1280 to 1380 wave numbers. And similar to the propylene glycol, for the 10,000 to 0, the 30-second average maintained the same relative predictive performance as the maximized 600-second average spectrum. Again, kind of a simpler model because we have a strong single peak. Was a single factor model with an average predictive error of the RM-SECV of 103 ppm. And then the determined calculated LoD to be 307 ppm. And again, smaller Raman cross section, more dilute sample, that results in that if any further reduction in the calibration range, 750 and below, did not provide enough spectral variation left in the data to generate a satisfactory multivariate PLS calibration model. The key takeaways. During method development and testing, one should consider is testing different averages as to their impact on the signal to noise, in turn affects the performance of the capabilities of quantitative LoD applications. So not to be considered. Now I do make it myself a standard practice when evaluating a given chemistry that we're looking at applying the technology to, is to start with smaller coads and then again evaluating what's the minimum for the desired predictive performance via offline, and then I have that information to take back and then use that to set up the instrument for future acquisitions. Two, the measurable detection limits in the range of 300 to 25 ppm are possible now with Raman spectroscopy. And they are possible with using a standard 500 milliwatt laser. So I mentioned that means you can use the impact class 3 laser. And you can do these possible limits with within acquisition times of 30 seconds or less. And this is important in that I've seen other, maybe potentially somebody could look at similar limits of detection, but then you need to be careful in looking at what is the power as well as the exposure time. I've seen other low detection studies where the power reported laser power was at 800 milliwatts and exposure times of 5 minutes to 10 minutes, which again leaning itself to the lack of implementations for real-time online process monitoring. In conclusion, Tornadoes Pro Plus enables new insights to help overcome these limitations, helping for companies to improve their quality, to gain better process efficiency, and deeper understanding of their processes for endpoint or optimization of these reactions. The superior performance enabled by HTVS allows for the monitoring of these applications far beyond the capabilities that are achievable with other process Raman instruments. So with that said, I'd like to turn that back over to our host, Omar, to discuss some other events that we have upcoming via some of the Tornado staff at various trade shows and conferences. So, Omar?
Thank you, Jeremy, for your excellent presentation. So we now have the pleasure of addressing our live question and answer session where today's speaker will answer your questions. And if you do have any, just as a general reminder, you can use the chat box within the menu. Let's take a look at the first question. What surprised you most about these results?
Actually, what surprised me the most was that I think I was honestly too conservative in my estimation of kind of the minimum required averages, and this goes to, again, the superior sensitivity that is achieved in terms of SNR of even just a single scan. I set it to 25, and that's what you see. Actually, I started off in 25 and went to the 15. As I already started acquiring some of the data and did some first pass calibrations, I'm like, I think I was too conservative of even initially setting 25. Like I said, with the lessons learned, I think, again, that I could go even reported better numbers in terms of minimum acquisition times if I'd have been less conservative in terms of my initial settings. So now that I actually, when I approach experiments that I'm doing now and in the future, I actually set it to a minimum of 10, then do my offline combinations to determine what the SNR needed for the desired analytical performance.
All right, thank you. Another question, how can I get more details about these experiments and the results?
Well, yes. Well, we have everyone's list of attendees and those that have an interest, and Omar can maybe weigh in as this as well. I have presented, which you can see on the list. I've actually presented this, or has been presented in a poster format at the SciEx show earlier this summer, and I will be presenting it again in the FPAC. So I think, and Omar, correct me if I'm wrong, but we can supply a copy of this presentation, but then also in the poster format provide some more text description to go along in terms of some of the background, some more details on the experiments and other things that are associated with the overall study.
Yeah, absolutely. Thank you. We will be providing a copy of the presentation to those attendees who are interested. Another question, how is a 10/100 ms accumulation different from a 1-second scan?
Well, it's really what I was defining is, in the end, it's people ask, because when they ask of what is the acquisition time, because that will impact, let's say for process applications, how much data will actually be acquired, and that, let's say the kinetics are really fast. If the the rate of change of the intermediates or starting consumption of the starting material or formation of the end product, let's say, occurs literally at the every 5 seconds, but the acquisition time, that means the ability to have data that you can track or quantify that, was to be 10 seconds, let's say, I'm making round numbers, there would be actual chemical changes. You'd be missing essentially the change in the data. So we have to determine the exposure, which is Raman is essentially when you're, unlike infrared, which is a ratio of you take the sample's not in the path, you map, you have the multi-frequency source, you have the detector. You first just take a background measurement, you take a sample, the energy is actually absorbed by the sample. So they're ratioing that what energy, essentially what percentage of the energy at given frequency has not reached the detector as a result. With Raman, it's a counting mechanism. So when the laser's off, there's no photons hitting the detector. When it's on, we're generating photons. So when we're saying signal strength, again, it's not to be this ratio against the background. It is actually photons. We're literally waiting and letting those photons reach the detector, and we're getting a count. So the longer that you wait, the stronger the peaks become, right? The higher the level. And this is the inherent advantage of HTVS, is that by comparison to other dispersive designs that may only have the total number of photons that are generated, again, when they talk about the laser power creating that Raman excitation, maybe only 5% of those ultimately reach the detector. With HTVS, we actually kind of invert that as well, that only we have maybe at most 4% loss to reach the detector through via HTVS. So 96% of the total photons generated by the sample reach the detector. So if you're in a counting situation, you've reached there much faster, right? You let so many photons hit, if you're counting, there's so many photons hit in much higher order of magnitude within a given time. So first we determine the signal strength, right? So that's what I said above, like when I said 300 milliseconds. Beyond that, I actually started reaching perhaps, approaching detector saturation. So I avoided that. Once there, that affects the analytical performance of the calibration is when you just take a single measurement, there's going to be some level of noise there. And this is where the averaging comes into place. If I average those, which I had done, like I said, in the one case of benzene, it only require the 25 average, but then for the acetone, when I wanted to go down to the lower limits of detection using the 750 and 250 calibrations, it took like 75, 3 combinations of the 25s to equal that, which was the 187.5 total acquisition time. So that says how often a data point that you would use to quantitatively predict against would be generated by the system. And so that's the rate of occurrence that you would use for training. And that's why I said you use both, in that we have the exposure, but on a given single exposure, which is a spectrum, and you can set the system to do a single exposure, you will have more noise, and the performance of the quantitative calibration will improve if you average those, which again, you take the exposure times the number of averages. This equals the total acquisition time of each spectrophile that you want to use for your analysis.
All right, thank you. Another question we have is, are there any additional experiments you'd like to try or retry to further this analysis?
Yes, a few of which is, one is getting in the test sets. Like, here I didn't test at something of higher fluorescence, so I could look at doing those. To really make those most applicable, it would be best to do that with like something like a biotech application, but then we do work with biotech companies, but often those things are in NDA that we inherently cannot discuss the data. So there's that's potential as well. This is where there actually is a lot of interest in the biotech community in our technology, and that there is an inherent amount of fluorescence, and as I talked about, one of the things that can limit quantitative limited detection is that the fluorescence can mask some of the peak information. There might be peaks there, but they're, let's say, partially masked. Well, this is again where it relates back to the averaging discussion, in that if you can create greater averaging, you reduce that noise. Even though the peak is small, you can improve the signal to noise by decreasing the noise level by further averaging. And with HTVS, and this is what people have the interest in ours, particularly in this sector, industry sector, is that the fast acquisition times give you that flexibility to then enable more averaging as each representative scan. If the exposure time requirements are on the order of, let's say, a minute, and you would get a better performance and reach lower detections by averaging 10 of those spectra, that's a 10-minute total acquisition time, and that might be impractical. Where if let's say our exposures are, instead of 1 minute, but like 10 seconds, an average would only be 100 seconds, right? A little over a minute acquisition time. So that's the advantage, that even the faster time allows for more averaging, which allows you for better prediction accuracy and lower limits of detection.
All right, thank you. We'll take one last question. Is the system also available for other laser wavelengths?
Our current focus, it's always as a company looking to diversify our portfolio. We have considered, the other laser frequencies, but right now we're focusing on 785. One of our engineers should, of course, speak on this even more so, but there is this relationship in both engineering and spectroscopy of going to different laser frequencies. You can go to a shorter excitation wavelength, like 532. You get more photon scatter, which means you could have a faster signal and faster acquisition times. The problem there, you get far more things that are fluorescent. You can go the other direction to 1064 that could produce far less fluorescence, but then they produce the lambda to the -4th power less photon scatter, so there's far less signal. The laser power mix, people usually try and compensate that with a higher power laser, but there's also the detector resolution. The detector, the shifts, the photon scatter is in the near infrared. The detectors need more cooling. They often don't have the same resolution. So the most applicable sweet spot for Raman spectroscopy, particularly for process application, is the 785 for the resolution, the photon scatter in terms of its signal strength, and limitations in terms of the amount of materials, in terms of being overwhelmed by fluorescence. So that really congruence of all those cost versus benefits do hybridize around the 785. But we do keep that option open for the future.
Thank you very much. Unfortunately, that's all the time we have for today. Please join me in thanking Jeremy Linoski for his presentation. For those of you who didn't have your questions answered today, all remaining questions will be addressed very soon. Before we sign off, a quick mention on some of our upcoming events. We'll be exhibiting at IFPAC in Bethesda, Maryland from February 27th to March 2nd. If you're planning on attending, please make sure to visit us at booth 209. Also, we'll be hosting another webinar in March. Stay tuned for more details. On behalf of Tornado Spectral Systems, I'd like to thank you all for attending. For more information on Tornado Spectral Systems, please visit our website, tornado-spectral.com. Thank you, everyone, and we look forward to seeing you at our upcoming events.